Tagliacone, who I guess with Informatics is going to maybe pull all this stuff together. And he'll reset the timer in a moment. You're okay.
So I've given talks with some pretty grandiose titles, and this one probably takes the cake. It's not really a revolution. It's more like a sort of a slow shift, if anything. But there's some people here, so I fooled some of you into sitting through this talk. I guess you could leave if you want. I'm going to talk about, but don't leave. There'll be some interesting stuff, I think. So I'm going to talk about reproducibility in the sense that for those of you who were here at the beginning when Martin distinguished between reproducibility and replicability, I mean reproducibility in the sense of being able to reproduce what it was that people did, right? So I'm not taking on the question of replicability in the sense of, is this a sort of a real result? How big is the effect, et cetera? I'm just interested in the question of, if someone tells you what they did, are you able to actually reproduce the steps they took independently of what the result might look like? And so I'll start by taking a sort of the sort of target position, if you like, this sort of what I call the do-it-yourself approach to neuroimaging, which is probably still sort of the most common approach. It's actually probably nearly universal. And all I mean here is that if you think about the way most labs go about individual studies, the typical procedure is you start by collecting some data, and then you use some off-the-shelf pre-processing and analysis tools, right? It could be SPM, FSL, various packages for pre-processing. Mostly based on GUI, so mostly you're sort of clicking through menus. There's usually some editing and scripting, so you might sort of batch a bunch of subjects, so you can do the same thing over and over quickly. And then, you know, when you do this for a while, and you save the data and the results on a drive somewhere. And you write a paper and you move on, right? So I think of this as sort of really the common approach, if you like. And it's a good approach. It works pretty well, right? There's no question that we learn stuff doing this. I mean, this has sort of been the dominant approach in cognitive neuroscience for a long time. And we publish a lot of papers. So we've learned a lot, we've published a lot, we have a lot of results. Nothing here should be construed to say this is sort of a bad thing to do, right? I mean, you start here. But it's still not ideal. And this might be compelling to you given some of the things you've heard in the previous talks, right? It's not ideal in the sense that doing things this way makes it kind of difficult, in some cases impossible, to replicate and extend results that have been published in the literature. So for one thing, data and code are often inaccessible, right? So I publish my finding, and you know, I tell you that I have some data, and you believe me, right? You don't think I'm lying that I made up the data, but I have the data, it's on some drive somewhere. You don't have easy access to it. There's often insufficient description of methods for practical reasons. You publish a paper in Science or Nature, and the editor says, well, you really need to cut this down to like 600 words. Very hard to explain what you did in an fMRI study in 600 words. And the result of this is that we end up with duplicated effort and wasted resources, because if you want to try and reproduce what I did, you might have to run an entire study, right? Or you might have to spend a lot of time understanding where my data is, tracking it down, sending emails, figuring out what formats it in, et cetera. Lots of errors go undetected because this is just time consuming. Most people don't have the time to sit around and just try to kind of work through what other people have done. So there's no question, there's plenty of examples you know, of errors just going undetected for years in some cases. If you're not worried about errors, you might worry about suboptimal processing and analysis pipelines, meaning, you know, for any given application, there's probably a best way to do things. I mean, there's many really good ways, there's probably many best, but there's better ways and worse ways. And chances are that someone out there has a tool that would probably be better for your application that you may not know of, that you haven't applied. And because it's very hard to access your data and reproduce it, et cetera, the odds of actually using the optimal pipelines are small. And you saw some evidence of that in some of the previous studies or talks. And also, I think concerningly, aggregation of expertise is very slow, by which I mean, sort of related to the previous points, we tend to think that different people are good at different things and have expertise in different areas. And so if you think someone is the world's expert in motion correction, right, and you know nothing about it, in some sense you would like to let that person analyze or you know, correct for motion, or at least try to take advantage of service they offer that allows you to correct for motion, instead of just pushing a button in whatever package you have in front of you. But it's very hard to do that when you sort of have this sort of do-it-yourself approach to analysis. Let me give you an example of an unreproducible finding. Okay, this is a paper I published a few years ago. I like the finding, I think it's interesting, so I'm not going to talk about it in detail, just to give you a sense of the idea. People were in the scanner, they listened to auditory narratives, sort of, you know, coherent stories, and what we showed, among other things, is that if you look at, for example, this region here, this anterior pole region, you have this sort of nice sort of linear increase, and the argument was that this is consistent with evidence suggesting that sort of you're building a situational model, right? So over time, as the story gets more elaborate, you have to maintain a representation of that. This may or may not be real. I think it is. I would like to believe so. But in some sense, it doesn't matter because I don't think anyone's ever going to be able to reproduce this finding, right? In the technical sense. Why not? Well, because I mean I, not the generic. Like, I don't have access to this data anymore. I could probably get it, but I'm not going to because it would take me a long time, right? It's on some server at WashU. I don't know where it is. It lives somewhere, but I don't have access to it. So if you ask me for it, I'm going to say, sorry, I don't have the time. And I mean well, I really do, but I just don't have the time to dig it up for you. The data are in an obscure format, so when I was at WashU as a graduate student when this study was done, we had our own way of doing things. Maybe they still do, I'm not sure. And so it's in a different space from everyone else's. The analysis software also is different from everyone else's. It's closed source, at least it was at the time. It's kind of opaque. The analysis scripts that I wrote are incomprehensible, as I recall, and they're scattered everywhere. Right? So at one time they made sense to me, but that was like 7 or 8 years ago. There's no way I could reconstruct what I did at this point. I use pre-processing pipelines that don't exist anymore. I'm sure that WashU has sort of, does things differently in 2015 than they did in 2008. There may be logs somewhere, but again, you don't want to go through those logs. I don't want to go through those logs. And I really just don't remember what I did, right? I believe what I put in the paper. I think, I did my best at the time. But the reality is, like, if you ask me to reconstruct this for you now, I'm going to, like, find some excuse not to do it because I just don't have that kind of time, right? So that's a problem. That is a big problem. You could try and reproduce my analyses, but you wouldn't get it quite right? There's just no way to reconstruct all the little things that I probably did along the way that I would not be able to, I could try, but I wouldn't be able to tell you. And you might, let's say you do this anyway, you put in the effort and you get a different result. Well, now the question arises, who is to blame for this, right? Is it my fault because I didn't tell you exactly what I did or because you couldn't reproduce what I did? Or is there a fundamental problem with the result, right? We don't know, and this is a deep problem because depending on which side of the ball you're on, you have a very different view of things, right? If you are your finding was not replicated, you tend to think, well, you just didn't do it right? There was something I did special that you didn't do. That's where the problem is. And of course, if you spend a lot of time, a lot of effort trying to reproduce someone else's result, you don't get it to show up, then you think, well, maybe it wasn't there, right? But there's fundamentally no actual way to reconcile that, right, to resolve that. Now, here's the really, really bizarre thing about this. I think this is really kind of, if you stop and think about it, this is really remarkable, right? What I just showed you is completely normal and acceptable, right? Like, if you look at most of the studies that probably most people in here have done, I think this would probably be true. So let's consider that, right? Unless you're willing to put in a lot of effort, probably nobody in this audience could reproduce most or possibly all of the papers that you have put out. They could approximate it, they could come reasonably close, but I think it's fair to say that you could not completely reproduce what you've done without an enormous amount of effort. And I'm not even talking necessarily about running new data. I'm saying, like, even if I handed you my data from that study, you still probably wouldn't be able to perfectly reproduce what I did, right? That is not a good situation to be in if you're a scientist and you think that science is built on the accumulation of findings over time. So it's kind of an odd thing to think about, that like, it's completely normal within this scientific community and most scientific communities to not actually be able to reproduce what someone else did. It's just par for the course that you shouldn't have that expectation. And I think we can do better, and that's sort of what I want to try to convince you of in the remaining time. Now, historically, I'm not saying there's no good reason for this. Historically, it had to be like this, because before we had sort of places you could put your data and gigabytes and gigabytes of data and different ways to share information and reproduce things and standards and so on. That was just the way it is. But I don't think it has to be this way anymore. We have the technology to improve every aspect of the typical workflow. And so I want to argue that we could have, and in many cases we already do have, perfect reproducibility and very easy extensibility with some effort, but quite easily. So I'll talk about sort of 3 ways that we can go about this. And they're not sort of necessary conditions. They're just sort of 3 strategies. One is to sort of adopt general best practices for scientific computing. There's nothing here that's specific to neuroimaging. I think these are things that lots of scientists should be and already are doing that can help sort of ensure reproducibility. Second thing I'll talk about is the Python neuroimaging stack. I am not suggesting that you have to do you work in Python for your work to be reproducible. Like, that's absolutely ridiculous. All I'm saying is that I think the Python stack has some advantages I'll talk about over other kind of ecosystems. But there's certainly other ways you could go. And lastly, I'll talk about sort of what some people have described as science as a service, the idea that we're increasingly moving away from sort of static tools that you run locally to services that sort of take an input from you and give you back an output, but do you're offloading the computation to someone else. So it's a service that you're consuming, essentially. Okay, so what do I mean when I say best practices? Well, here's something that happens, a kind of thing that happens a lot to many of us. You lose your analyses to a hard drive crash, right? You did these analyses and then something bad happened and you don't have that anymore and all your work is gone. How many people have had this happen to them at some point in their career? You can be honest, you can raise your hand, it certainly happened to me. Not that many? Okay, that's good. That's okay. I stand corrected on this one at least. How about this one? My script doesn't work anymore. It worked at some point, and then I changed it at some point, but I don't know what I did, and now it doesn't work. How many people? Okay, almost everyone, or most people, all right. What about this? Someone asks you for the data, or maybe you're trying to reconstruct your own sort of analysis workflow at some point, and you realize that this is kind of a mess, and it would take you like a month just to figure out what you did, and so you don't do it. You move on. How many people will? Okay, so now almost everyone will admit to this. Okay. So the point being that there are these common problems we run into that cost us a lot of time. They make it hard to reproduce our own work. And the thing is, we have the tools to prevent this. And a lot of them actually come out of the software development community, because software developers are very methodical people who like to spend some time up front to make their life easier in the long run. And I think a lot of the open science community is starting to adopt some of these practices. And they can really make a difference, and they're not actually that hard to implement. There's a short-term, long-term trade-off, so you spend some time up front, but it can change your life, really, in the long run. So I'll talk about a few. So one is formal version control. So when I say version control, you might think I just mean like, well, you have a Word document and then you hit save as and you append the date and your name, and then you send it to your collaborator, and eventually you have this 500 character long name, and the record of what was done is in that and who edited it, right? That's a version of version control, but it's not what I would think of as formal version control. So the idea here is really that you could track any and all changes to your data, to your code, to your materials, your manuscripts, or whatever. And there are many, many ways to do this. I would say probably the most common one is to use something called GitHub. How many people have heard of GitHub? How many people use GitHub regularly? Okay, so many people have heard of it, fewer people have used it. GitHub is, I'll show you in a second how it works. There's also something called the Open Science Framework, which is newer, which is sort of geared towards scientists, and in many ways is simpler. So I would recommend you take a look at that. It's very easy to get into and serves many of the same kind of functions. But here's how version control in the formal sense works. So you have a repository, which is sort of the gold standard. It's the current state of your project, and project can mean data, can mean code, can mean whatever you want. And you have multiple users potentially, or possibly just you. But the idea is that whenever you want to make a change to anything, you actually have to check out, or you sort of request from that repository the current state of the project. And then it sends to your sort of local repository that code or data or whatever, and you make changes locally, you edit them here, and then when you're done, you say, okay, now I'm ready to commit this change so that there's a permanent record of it, you push it back up to the repository. And the beautiful thing about this, other people can do the same thing at the same time, and there's lots of ways to resolve potential merge conflicts, etc. But the idea basically is you should never, ever lose a change you have made. And in fact, there's always a record, a paper trail, if you like, going back since the beginning of time, since the beginning of the project. And GitHub is sort of built on something called Git, which is a platform that implements this kind of thing. But it's public, so that you can actually do this all in the open. Or if you want, you can pay them just a little bit of money, and you can do it privately. So you don't have to show everyone. You can use the tools without making them public. Although most people end up being okay with making stuff public. So here's a project, and I'll talk about NiPipe in a couple of minutes. This is a Python package for sort of building workflows and interfacing between different neuroimaging packages. I'll talk about it in a bit. It's a complex display, but what you get here is a bunch of things. So you can see, for example, that if you look at the commits, there's almost 7,000 discrete commits that have been made, meaning people have registered a bunch of changes 7,000 times in this project. And you can look at the history at any point in time, right? So you would never lose. You can always go back and say, well, on June 17th, 2013, here's what NiPipe looked like, right? And you can, if you want, you can clone the repository as it was at that moment in time. It has different branches, so someone can say, well, I'm going to start some completely new feature. I might muck around with some code. I don't want this to affect other people. I create my own branch. Later in time, you can merge them, so you can sort of say, okay, now I'm ready to bring this back into the main project. So you can manage things nicely that way. The thing I want to highlight most, though, is this. 77 contributors, right? This is a project that's been around, I think, 4 or 5 years. It has 77 unique contributors, and most of them are really, there's not like, so Satra is the sort of, is the creator of NiPipe, and it's not like these people work for Satra or were students or anything. Most of these are people who independently said, hey, I have something to contribute to this project because I can get something out of it too, and make a contribution. And this is very typical in the open source ecosystem, right? So one very good reason to put your code on GitHub is because other people might actually write your code for you and help develop it. It has a nice issues interface, so sometimes your code has bugs, unfortunately, and it's nice when people can tell you that in a way that you can sort of track easily. So here's, someone saying, they found a potential problem, And if you scroll down, there's a discussion thread, and that link directly to the code changes. So you have this very nice way of tracking everything that happened. And again, this is not true just for code. This can be true of your analyses, of your papers, whatever you like. If you want to know exactly what changes were made at any given point in time, here's one commit. I don't know if you can see the colors really clearly, but the point is that it highlights for you what changes were made, what lines were changed, right? So you can always go back and say, oh, here's what was changed. Now, it doesn't do this, as far as I know, for like Word documents, but if you're working in LaTeX, for example, then you do get this. And so you can actually see, okay, I sent the paper to my co-author, and these are the changes they made, and that will never go away, right? You'll have that record forever. And so you can always reproduce what happened. There's no reason why you should ever lose changes you made to a code base or data, et cetera, again. Okay, so that's version control. This is a sort of even more recent trend, interactive notebooks. There's many flavors of these. What I'm showing you here is an IPython, or now it's called Jupyter Notebook. How many people have seen IPython or Jupyter Notebooks? There's variants in R and other things. Okay, not that many. So the way to think about this is it's sort of your lab notebook, but in digital form, right? So you can think of like you might have a record of all the things you did, and then you might have like sketches. And what this is sort of a modern version of that, where you have now the text, a description. You can write descriptions to yourself or for other people. You embed the code, and then you can run the code and generate the results. And so here's an example. This is from a poster, so shameless self-promotion. This is from a poster that Tim Rubin and I have on Thursday, I think. And the idea here is that here's a chunk of code, there's more you're not seeing, that generates this figure. And so you can download this, run it, and assuming that data is embedded, it's perfectly reproducible, and you have a description embedded. So I would argue something like this is probably the future of publishing, in the sense that, why have the methods here and then like the data there, and then you have to go and reconstruct things. We are very close to having nice interactive web-based, essentially publications where you can reproduce everything start to finish and create the images from scratch if you like, and see what happens if you tweak one or two things. Virtualization is another really important trend. So we all know that there are differences across platforms. There's been some, commotion about certain packages in recent years. That, like, some packages, the same package nominally does not give you the same results when it's running on a Mac versus a PC, right? Imaging packages. Well, that's a problem. There is a way around that, which is to virtualize. And what the idea is this: historically, what you had was the classical architecture. You have some hardware. On top of that, you have an operating system, and then applications that run under that operating system. And what virtualization does is it gives you this sort of virtual layer that you can install on any operating system, and then within that you can run this sort of encapsulated version of the architecture. And so in theory, what happens is, if your code and your analysis and your results are all sitting in here, anybody should be able to perfectly reproduce, right? Not sort of, there's no luck involved. They should be able to perfectly reproduce everything you did. So it's a completely reproducible environment by definition, right? If I send you a disk image, it should run exactly the same for you as it does for me. Now, it may not run at all, which means you have some technical issues to resolve. But once you do that, you should have exactly the same setup, and you should never have to, you should never be in a situation where someone says, well, I couldn't get this to work on, a Mac, even though it worked beautifully on a PC. So that's the ideal. And this is starting to be much more common, too, where people are now releasing sort of, Docker images or Linux disk images that have everything you need to exactly perfectly reproduce the analysis. And I think we'll see a lot more of this in imaging, too, in the coming years. Okay. So let me shift gears a little bit and talk about the Python neuroimaging stack. So what I'm talking about here is an ecosystem of interlinked tools and platforms for doing neuroimaging data analysis written in Python. Now, as I already mentioned, I'm not making the argument that you have to use Python, right? There's lots and lots of alternatives. You can do, the reality is you can do everything you want in various environments, but I think Python has some benefits, particularly if you're starting out and you're trying to come up with, you're trying to decide, well, what should I use as I sort of start my research career. So why Python? Well, one reason is it's a high-level, dynamic, easy-to-learn language. So it's reasonably performant, but it's still very easy to learn. You don't spend a lot of time doing things that, like in lower-level languages like C, you might have to handle like garbage collection and memory allocation. So you can really write code that looks very sort of almost human-like. I mean, it's never really human-like, but it's sort of closer to what you might expect to see as a description of what's going on. It's been described as the second best language for everything. So the idea is, in any given application, sure, you may find some other language or environment is better, but the nice thing about Python is you can do almost anything really well. And that counts for a lot, because it means you can work in one language for almost everything you do. And so I haven't really used almost anything else in 4 or 5 years. Not because I insist on using Python, just because there's just less and less reason to fall back on something else. It's free, it's open source, community driven. So as I just showed you, most of these packages are written by people like you. right? So they're community-driven. They're not proprietary. You don't have to pay anyone to use any of these tools. And again, there are many alternatives. The only argument I'm making is if you're trying to pick, one sort of environment to work in that you can probably stay in for the rest of your career, the Python stack is probably a good place to start. If you've spent a lot of your career already working in MATLAB, R, these kinds of things, then probably there's less incentive to switch. So I'm not saying, go ahead and switch to Python. I'll give you an example of one umbrella organization called NiPy, which is a loose confederation of these kinds of packages. So there's things like NiBabble for reading and writing images really efficiently, handle pretty much any format of neuroimaging volume you can think of. NiPy does analysis of structural and functional data, so it'd be sort of FSL equivalent, although it's, I think, sort of not that widely used anymore. PyMVP and NiLearn are two nice machine learning packages, so you can really quickly and easily do very sophisticated machine learning analyses in Python. DiPy is for diffusion fMRI, and so on. And there's a bunch of others. I will focus on NiPy, which I talked about, because I think if you're talking about reproducibility, this is I think of this as sort of the state of the art in neuroimaging, right? So what NiPy does is it allows you, it's sort of the glue. It allows you to bind together all kinds of different neuroimaging packages, not just in Python, right? FSL, SBM, FreeSurfer, you name it. No matter what tool you're using, if it's widely used, there's a good chance there's an interface for it in NiPy. And so the idea is you can actually create these workflows that stitch together all these different tools, and again, are completely reproducible. It's one script that tells your computer how to interact with FSL. So okay, you pump these images in, it'll do the pre-processing, then it'll come back, and you can send them to a different analysis package and build very complex but very reproducible workflows. So it's a very kind of nice approach. Last thing I'll talk about is sort of the idea of a science as service. So many pre-processing or processing analysis steps involve predictable transformations of data, right? And so I already talked about you can do these kinds of things locally, which is the way we've traditionally done it. But you could argue that a lot of these things can be centralized and turned into web-based services, where I just ship the data, you do the best thing you can, because that's what you do, right? You have the service you provide, and you give me back my data. And if I want to, I can find out exactly what you did. So it's not like it's a black box. But I don't have to do this locally or handle the infrastructure, et cetera. And we're seeing an increasing number of neuroimaging services like this, both GUI-based, meaning you have a web interface you can work in, and API-driven, meaning you can programmatically interact with the underlying data or tool. I'll give you just a few examples. Oh, and the nice thing about this is if you don't code, right? So if you might say, everything I've talked about so far is great, but you have to have some programming experience. And maybe that's true, but you don't really necessarily have to have any programming experience to use some of these tools. And I think this is sort of going to be one of the coming waves of data analysis. So here's one example you may have seen, OpenFMRI. This is a project developed by Russ Poldrak's group. There have been repositories in the past, going back many years, so it's not a new idea, but there are some nice things about it. So you can see right now it has 37 data sets. These are raw fMRI data sets, lots of subjects. So you can give them your data, and they will help you standardize it. So they will actually do a lot of the work for you, or work with you, to put the data in a common format. And so when you go and access one of these data sets, and there's lots of them now, you pretty much know what you're getting. They're well documented. They're in a sort of standardized format. And so you can come along and say, well, I want to use this classification, learning, and tone counting task and do some new analyses on that. Right? So it's a valuable service to the community that allows you to deposit and access data for free. But that's raw data. What about sort of results? Right? So you've already heard a little bit about NeuroVault. NeuroVault is a project also out of, now Russ's lab, developed by Chris Gorgolewski. And the idea here is now you're only uploading the statistical, the Z-maps, which Tom Nichols mentioned. So you did a study, you want to share your results, you can put them online. And for free, I mean, this is the beauty of it, you get a nice sort of 2D and 3D interactive visualization of this. You can actually navigate around your image. You can send the link to someone out there and say, hey, here's my image. And I think what people will start doing eventually is putting these in paper. So like, why have a static slice of the brain where you can just link to a 3D, 2D image, and people can navigate it for themselves and download it, right? So, yeah, thanks. And finally, I'll talk about Neurosynth, which is my project, and Tori mentioned this a little bit. And so the idea here is so let's say you have a bunch of data and you want to sort of make some sense out of it. So what it lets you do is sort of based on a very large accumulation of the literature. So in this case, we're now almost at 11,000 studies. You can do fairly crude, but sometimes useful meta-analyses. So here's, for example, what a fully automated meta-analysis of reward looks like. You can do other things. We just introduced functionality to do custom analyses online, so it's very crude and it's a little bit buggy, but you can now actually do your own meta-analyses using our tools online, so you can select different studies. You're not restricted to the terms we give you. And as already mentioned, I'll skip over this because you can sort of you can upload images to NeuroVault and instantly decode them. So you have a sense of what's going on in your image, subject to lots of caveats and qualifiers. Okay, so those are just some examples, and I do want to emphasize that there's lots and lots of other resources, right? So the point here is not to say these are the tools you should be using so much as this is, I would like to believe, and I think it is, sort of the way of the future in the sense that we are going to see an increasing shift towards these kind of service-oriented platforms where the people who do one thing best are the people who should be doing that thing for probably many people, if not everybody, and you can take advantage of that really easily. And that makes everything reproducible, ultimately. So this is just a slice of the cake. There's lots of other resources. Okay, so last thing I'll talk about is where we're headed. This is where we're headed, Waikiki Beach, right? So hopefully after the festivities, you're all going to spend some time on the beach. And after that, we're hopefully headed towards greater openness and transparency at all stages of the analysis process. I think we will see rapid adoption of computing practices, and we're already seeing this actually in many fields, including neuroimaging. These practices that enhance reproducibility. They also make life better in lots of other ways, but for present purposes, they make things reproducible, right? It's very hard to lose track of what analysis you did when it's on GitHub. The tools interoperate with one another seamlessly, so you can sort of ship them back and forth. You don't have to sort of, later reconstruct, did I use this tool, did I use that tool? And we're moving towards, with something like NiPipe, for instance, fully reproducible, automated, and integrated data workflows so that you can see exactly what's done start to finish, and there's a permanent record, and you can send that to anyone, and they can reconstruct that themselves. And lastly, I think web services that enable easy sharing, pre-processing, analysis, visualization, interpretation of results. There is, I think, going to be a trend towards doing, taking advantage of these services online rather than everyone having to duplicate the effort locally. So I decided to acknowledge everyone because what the point of this is, of course, people are responsible for different projects, but if you go and look at something like NiPipe where 80 people have contributed to the code, it's very clear this is a community, right, that's building all these things. And everyone who contributes to any of these packages and anyone who registers an issue and says, here's a bug I found, deserves some credit for the success of these tools and the community as a whole. So I think if we care about reproducibility, we should start thinking about some of these practices, even if it's just changing what you do a little bit. I think the sort of the global effect is going to be bigger than the sum of all the parts, to be a little bit corny. So I'll stop there. Thanks.
Okay, so we're about 5 minutes behind, so we'll have now 10 minutes of question, discussion, whatever. We could probably go on for several hours, of course, but I think 10 minutes we'll have to do on this occasion. So now we've lost a couple of the speakers. Some of our guys are popular and they are in other sessions, but doesn't matter. Ask the question, we'll try and interpolate if the relevant speaker's not here.
I would just like to thank Tal for his talk first. I think that's such a great overview of and such a great perspective as well on our field. It's something that I think many people care about, that we change our culture, and that's one way of changing our culture of science and neuroimaging, which is going this direction. I think you still put a lot of the problems under the carpet, and there's I think one of the things that most likely is going to happen is that we will need to train ourselves in sort of computational tools and techniques, and Git is one of them. GitHub is just the thing that's hosting some of the project, that Git project, but Git itself without GitHub is just the thing that you probably need to start with. And I would like one question that you posed, ask one question to you is basically what's the, what do you think are the problems, the most likely problems to go where you want to go, and I'm pointing maybe the funding problem, and how do we fund how do we fund projects that are across so many labs, and that's one issue, but there may be others that you can think of. And
so I think I had a mixed feeling about the funding problem. So this came up yesterday at the hackathon for people who are there. I think. In some ways, it feels like this kind of work should be, it should be easy to get funding for it because the argument is very clearly like, look, why should everyone do the same thing over and over and over again where we could have one person or a few people providing a service for everybody? And my sense is that actually that argument does work. So I think, if you look at the numbers, of course, times are hard for everybody, so everyone has a hard time getting funding. But I do think that there is an appreciation, broadly speaking, that if you can say, look, here's a tool that a lot of people can use, and I can show you, and here's people who say that this has been useful for them, I think the funding agencies and reviewers are sensitive to that. But that's within the context of hard times for everyone, so it may not feel that way, but that's sort of my sense. So I guess I'm optimistic in that sense. I think that we are sort of having some impact using these tools.
I think distributed funding across laboratories is still a difficult thing.
Yeah, I guess we won't pursue this, but that question raises a bigger issue of what kind of infrastructure your team should assemble in order to pursue all the issues that have been raised in this workshop. Perhaps something to talk about later, but we'll take the next question.
I have a question about the processing pipeline, the use of spatial smoothing. There were two lecturers, I believe, Dr. Gallant today and this morning, Dr. Jenkinson, who were talking about either not doing any spatial smoothing or reducing the kernel size of spatial smoothing. And I wonder about that because, as you know, one of the best ways to improve the signal-to-noise ratio is through averaging. And if you're going to be doing group comparisons and you're not doing a lot of spatial smoothing, then my intuition is that you're going to lose a lot of the signal through a lack of averaging if you're not spatially smoothing. So I don't know who's best. Is Dr. Wager here?
I'll let Steve have a go. I think
Okay.
a number of us have got strong opinions about that, but we shouldn't use up all the time giving them. Yeah, you'll have to come up, Steve, yeah.
I guess I'm a little agnostic, actually, about spatial smoothing, because to me it's just a parameter I plug into my pipeline and then try and optimize it. I'd make two comments, and maybe someone else will then pick it up. One is that there's no single best kernel, so that's a problem with the spatial smoothing we're currently using, because as you know, a small object needs a relatively small smoothing kernel, and a large object needs a large smoothing kernel. And we have done a little work in spatial smoothing, and actually if you optimize all those pipeline steps I talked about, you get a heck of a lot more with no smoothing than you do using our current procedures. So one way of potentially trying to deal with the smoothing issue is to try and optimize everything else. And then maybe you're going to be able to push the kernel well down. You're still going to have the problem of aligning activations across multiple subjects. So you still have the registration problem, and a bit of smoothing for imperfect registration is helpful because it helps the activations across individual subjects overlap.
Okay, I think that'll do for that one.
Steve, just in Steve's presentation, you mentioned a little bit about the imaging biomarks, and it's actually it's very important issues. But my question for everyone, like in most disease studies, in the publication most people only report where they find the activation difference between patient and the normal control, but not many report how much the difference is. There's still a lot of question yet to find the answers. Like one is like how to define ROI to measure the difference. Like should we use anatomic ROI or functional ROI? Should we define the functional ROI individual basis or the group basis? And even we have ROI. And then another question, should we do the model like GLM fitting on average of the signal, or should we fit in every voxel and then summarize, calculate average of the contrast or the other numbers? That is leading to another question. I'm always thinking about
Well, okay, I think two is enough. Okay,
yeah.
So we'll let Steve go at that.
Okay, again, I would say that, neuroimaging is fundamentally an optimization problem in a very high-dimensional space, and you're trying to find a set of choices in that space that will get you close to the target, which I guess, unfortunately, is getting a paper published in many places in our community, but hopefully many of us still feel there's a scientific truth that we're sort of after there as well, which is what the optimization process is about. So I don't think until I know what it is the goal of your study is, I could tell you what it is you should optimize. Now, I've used a couple of metrics, prediction and reproducibility, as an attempt, as sort of surrogates for general optimizers, but I certainly wouldn't claim that they are the things everyone should necessarily optimize for their particular study. I think I know I'm not exactly answering your question because it doesn't have a single simple answer, unfortunately. So, and partly we're going to, I think, solve some of these problems with the things Tal has been talking about, because you'll decide to do it one way, which makes sense to you, but your data will be readily accessible to other people who are doing it another way, and it will become very easy to compare across different sets of choices in this high-dimensional space. And ultimately, that may be the only way we'll actually ever optimize these sorts of choices. We may find there are certain classes of study where you need to make one choice, and another class where you need to make another choice. So this tendency to try and find the right answer for many of the things we're trying to do, I think is probably heading in the wrong direction. I mean, I hope I'm wrong in that there is a reasonable set of sort of almost right answers, but I don't think it's at all clear yet in neuroimaging in general, across all the sorts of studies we're doing in the brain, when we know so little about both our signal and what's actually happening in the brain itself. Anyway.
Look, we're running out of time. I'm going to take one more, but I'm sorry, not from you. You've already asked about 3 or 4. The gentleman behind. This will be the last one.
My question is also to Professor Strother. When thinking about individualizing the pipelines, which is, I think, an idea that would change the pipelines in many labs, what is the exact reason that the switching on of certain steps sort of disrupts or reduces the power in some subjects? Because to my understanding, it comes to certain regressors in the GLM in the end, and having hundreds of images usually robbing some degrees of freedom cannot be the reason. So why are some steps sort of disrupting the quality of the analysis?
I'll give you 2 examples. So one is motion correction, which most people think they should always switch on. But in fact, the way the cost functions work in motion correction, if your subject has no motion and you have a task in there, what the motion correction cost function will actually grab on is the task effect and then attempt to adjust the images to reduce it. So in fact, it's going to suppress your task effect. So whether you need motion correction or not is actually a function of the amount of motion you have in your data. So it's conceivable, and we have seen that in some of our subjects, we don't turn motion correction on. And this has been in the literature. Frere, I think, has a paper in 2001 where he first pointed this out. And they actually ran a process in their lab where I think as if they had, I mean, maybe Jean-Baptiste remembers this.
Yes, but the cost function was bad at the time. The cost function has changed.
Okay, so the cost functions have improved just to make our life harder, but it's still this issue that if you have no motion, they're still going to tend to remove a bit of the signal. And the other thing is motion parameter regression. We've published a paper in 2012 where what we found that in the subjects that move quite a lot, it helps, but in the subjects that move a little bit, and that was dependent on a median split in a particular study, it made them worse. Because again, you're tending to regress something out. If you regress something out that you don't need to regress out, then you're essentially overfitting your data. And you may both be removing something you don't need to remove and chewing up degrees of freedom.
Okay, so we'll wrap it up. I guess I just make a couple of quick comments. I think every single one of the speakers has given you some very specific things that you could actually do. You may not be able to do them all. There were 7 talks. It's a lot of stuff. But there were some very explicit things there. So I think there's something for you to work on, maybe one at a time, over the next 12 months, shall we say. In any case, I guess it's time to maybe not quite head for Waikiki, but call it quits. So I just thank all the speakers and thank you for coming.